Okay, so all we got to do here, have a look. So if we're taking limits as x approaches negative infinity, all we're going to do here, where do you even see x's? Well, inside the log, right? So inside the log, as x goes to negative infinity, what's going to be the limit of that rational function?
1.
1. Okay? So that whole thing is going to 1. And so this is equal to, in the limit, this is equal to negative 7/5 plus the natural log of 1. Okay, what's the natural log of 1? And you can think of it in terms of the function, and you got to know what the log function looks like. So let's review that from last year, or the year before. That's been a long time ago now. So what does a natural log function do? Okay, but what's it look like?
It goes up.
But how?
It comes up and goes like that.
Okay, so a log function grows more and more slowly with, as x increases, right? You can log in. Yeah, go ahead. You can. That's fine. So it's going to go up from negative infinity, right? It's asymptotic on the y-axis. So it's going to do this. And where does it cross the x-axis?
1, 0.
At 1, 0, right? So it crosses at 1, 0. How do you remember this? You remember this because what's the inverse of a log function? So this is log x. What's the inverse of a log function? Base E exponential, right? And so a base E exponential, you know what that looks like, right? That one's base E exponential looks like that, right? Okay, where does it cross? Well, it crosses, if this is the function f of x equals e to the x, what's anything to the 0? 1. So you know this one's crossing at 0, 1, right? And so you know that these two functions have to have symmetry because they're inverses. They have to have symmetry about the line y equals x, right? And so you can always make that connection. And once you've done it like once, you'll just remember this function. Right? Okay, so what is then, based on this graph, what is the log of 1?
0.
0. So what's the answer? Negative 7/5. Okay, what's the moral of the story here? Why is this an important problem? Because when you're analyzing, you're taking a limit of a composition of functions, that's okay, right? You're just taking the limit of what's inside and then evaluating the outside function at that place, right? You see that the rational function is actually inside of a log function this time. It's okay. Same rules apply, right? We're still just taking the ratio of the leading coefficients here because the polynomials are same degrees, right? Okay. How else could you convince yourself what the log of 1 is? That's a base E, right? If we set that equal to x, a log is an exponent. So how do I? Exactly. E to the x equals 1. So what does x have to be? 0. Okay. There you go. Good. Okay.
Wait, okay, but there was one with the actual log.
Okay.
The LOG.
LOG. Okay. Can I just pull yours up, Katie? Oh, come on.
Oh, wait.
So, oh yeah, you don't check the messages?
No, I don't check my messages.
Jill, do you send them messages?
Ask my daughter how many unread messages I have on my phone. It's embarrassing.
There was one, like,
I'm not good at that. I'm too busy for that stuff. Too busy writing custom calculus problems for you guys.
How do you even write 1,000?
Yeah, how do you even come up with that?
How do you even write a custom calculus problem?
Let's see here. Probably at the bottom, I'm assuming. Yeah.
Yeah, one of them.
Okay. Down.
There.
Right there. There's a good one right there.
Okay.
What do you
Oh
know?
my gosh, you guys all have like 2 attempts on some of the problems. I have like 50 on some.
You can see how many attempts? Oh my god.
Yeah. And I can even go,
Embarrassing.
if I want to go back and see a prior attempt, I can just do that. Actually, that's the same attempt.
Yeah, see, log. Oh.
Yeah.
Really, I was
Okay. Same kind of thing. As x approaches infinity, you tell me, what are we gonna do here? JJ. 10 over 1. Everybody agree? So we take the limit of the rational function in here, and that's just going to go to 10, right? And so we evaluated our limit. That's all we had to do. Now we have to simplify this. We get negative 7/2 plus the base 10 log of 10. What's the base 10 log of 10? 10 to what power is 10? 1.
Oh, that's what that means?
Okay? Did that work?
That's the first one.
HH. Right? We good? Okay? Okay. All right, so what I do want to do today, and I'll give you this, it's an online, the Math Excel test is online. I'm willing to give you multiple retakes on that, so if you want to, I'm okay with that. I'm going to obviously move on, but I don't mind doing that. Yeah.
So do you think since I started my test, we'll still be there after they have the crash?
I'm sure it will be. Yeah. This happened one other year and everything was fine. Yeah. So I think it will be. I think it will be.
So I was almost done, I thought I was gonna be good, but kind of worried about it.
No, I think it'll be
I don't think
fine.
you lost it.
I think it'll be fine. Your accounts didn't go away. I think just somehow, I don't know, somehow that they have to probably give us a new code. Or something. So I'm sure it'll be fine. Pretty sure. Okay, so here's what I want to look at today. This is really cool stuff. We're going to move on to, the topic is derivatives. And this is this is really important picture I'm going to draw here. This is how you relate to, this essentially is differential calculus in a picture. This is what it's all about. So if we take some function, call it f, and our goal is, this is the whole point of this. And if I didn't think I was doing this today, so I would have had a nice little Desmos dragon, sliders and all that kind of fun stuff, but you have to do it without, because I didn't plan on this either. If we want to know at some point, and let's call it, I want to make sure I'm doing what's in your textbook. I think they use X's and H's, but every book does it a little different, so let me look here. Okay. Okay. Okay.
Oh, yeah.
Yeah.
Okay, if I want to make an estimate of what the slope of the tangent line is at x, that's our goal. Okay. What does that even look like? If I want to graph the slope of a tangent line at a point, what are the characteristics of a tangent line? Say it again. Well, most lines are linear. That's true. What else? What else? Let me tell you. Tangent line. Characteristics of a tangent line. Tangent to a curve. Not like, we're not talking about a trig tangent function. Yes.
It has the same slope as the curve at that point.
Okay, so it's gonna intersect the curve at only one point, but something like this still doesn't fit the criteria. That only intersects it at one point locally. It might graze it at other places too, but that's incidental. We don't care about that. Locally speaking, in the vicinity of our point, it's only intersecting in one point, and it's got to match the curvature of the function, right? So it's going to be this guy, right? We want to find the slope of that. That was a huge, seemingly intractable math problem for centuries. Finally, this was this was the beginning of calculus, is when people came up with a technique for solving that problem. Any suggestions? Yeah, I got a question for you first, and I'll ask you again in a moment. This seems like an unrelated thing, but let's say that we want to make an estimate of how fast our car is going when we pass by a Rue elevator on the way to, where are we going? Like Fort Worth, right? Okay? I could say, okay, it takes me, let's not make it boring, that's inconvenient. What's 60 miles away? Arlington? Pretend it's 60 miles away. So if it takes us 60 minutes to get to Arlington, what's our average speed? 60 miles an hour, okay? Is that a reasonable estimate of how fast we're going by Rue elevator? I mean, probably not. I mean, it could be better. How could we make it, you know where that is? I just learned this recently. That's that when you drive to Hermston? Yeah, it's right, that one up on the right, that big grain elevator, this old, looking thing. So what's maybe a way we could get a little more accurate estimate? Our speedometer's broken, by the way.
Shorten it down.
Okay, so what if we instead, okay, let's say, okay, now let's only measure, we'll take the mile markers that include Rue elevator, and we'll measure that 1 mile. Okay, let's say we find that it takes us 60 seconds to go that 1 mile. Okay, it's still 60. Is that a better estimate than?
Yes.
Okay, everybody agree? Because we don't know, that over the course of a trip to Arlington, our speed's gonna vary quite a bit, isn't it? Right? Probably much better over the course of a mile. How can we get even better? Short. Make it 100 yards, 100 meters, something, right? Better yet, make it really short. We'll put some photo gates out there, we'll only go a meter. Right? And measure how long it takes us to go a meter in our car. That's pretty accurate. A car's not going to accelerate or decelerate, hopefully, much over the course of a meter. If it did, it probably wouldn't be a good thing. So you get the idea. If we wanted to invoke the concept of a limit here, how could we get a perfect, using the concept of a limit, how could we get a perfect estimate of what our speed is right as we pass by the front edge of the elevator? And what are we gonna take the limit of here? Think what we've been doing. If we went from Pendleton to Arlington, we're take a mile instead. So it's gonna be the distance we're traveling in the limit that's going to 0, right? Then we're gonna get effectively a perfect instantaneous speed when we pass by Rue elevator, right? Okay, let's apply that to this problem. It's really the same concept. If I take some secant line, now what's the definition of a secant line? No, it's different. This isn't we're not talking, so we're separate from trig stuff now. A tangent line and a secant line are completely separate things. I know in math we reuse words all the time and it can be confusing. After a while, the context makes sense. So we're not talking trig functions at all.
Secant would be perpendicular.
No.
No?
A
Okay.
secant line, so you guys haven't heard this. I was just curious if you'd ever heard this before.
No.
Okay, so we haven't. So here's what a secant line is. A secant line is a line that connects 2 points locally. Okay, so a secant line, this purple line, is the secant line connecting the points with coordinates x, f of x, and what's this one gonna be? If the second point is, we'll call it delta x, and remember, delta just means change in math, right? So we're gonna change our x value by some amount we'll call delta x. So our new coordinate is just x plus delta x, whatever that amount is. That's how much we've changed our x value. Agreed? So what are the coordinates of this point gonna be then? X plus delta x,
F of x is that.
f of x plus delta x, right?
Yes.
Okay. So if I'm connecting those 2 points, the secant line is telling me the average rate of change, isn't it? Think if I draw a slope triangle here, based on these 2 points, here's a point and here's a point, right? Right triangle. Well, the horizontal length of this triangle is just delta x, isn't it? right? It's the change in x, which is x plus delta x minus x, delta x. What's delta y?
Change in F.
Okay, it's going to be the change in y, which would be the difference in the values of the function, right? So if we look over here, let's just put these values on the y-axis. Here I've got f of x, and here I've got f of x plus delta x. Well, delta y is just that distance, isn't it? Everybody see? Right? So delta y equals f of x plus delta x minus f of x. Right? And the slope of the secant line is just telling us, well, the ratio of delta y over delta x. It's just the slope of a line. Okay? So we could say then that the slope of the secant line is delta y over delta x, which is just f of x plus delta x minus f of x over delta x. If I pick some, let's actually do an example. Let's do an example on Desmos. This is what I kind of wanted to have already done, but you'll forgive me. So if we take the function f of x equals x squared, how about? Instead of using x's this time, I'm going to use, let's call it c. Our initial x value we'll call c. C equals 4, and we'll use a slider, how about? Okay. I don't think I can put delta x on here. So I'm just going to call it, for delta x, I'm just going to call it d. Okay? That means delta x. Actually, I didn't think about this. Oh, I don't see it. Oh, never mind. Not worth it. So d equals okay. All right, so let's take the point then. Let's take the ordered pair C f of c. Okay.
Yeah.
And oh, what the heck is it doing? This is doing something weird.
You put the comma in the word F.
Darn it, anyway. Let's just pick a value. So C is going to equal 4. So I'm just going to put a 4 in there. Okay. Oh, let's make it smaller than that though. 1. It's too big. There it is. Oh, maybe that's what was going on. That's what was going on. The C slider. Oh, never mind. That's all it was. I'm just being a dummy. I should have just done this. Oh, there we go. Okay, perfect. So there's CF of C. All right, there we go. We're happy. So there's CF of C. Now, if D is 2, let's find the other point. So the other point is going to be at the ordered pair C plus D, comma, F of C plus D. Okay? And let's...
D represents delta x plus...
Yeah, D represents delta x. Put that in your notes. D represents delta x. I guess it's on video too. It's there. Okay, and so we can now let's go ahead and connect. Let's connect those points. So let's create the equation of that line. I gotta just think here real quick. Maybe you guys could help me out. So the equation of the secant line then is just going to be, it's just going to be y minus f of c. I'll just use point slope form, equals the slope, which is, oh my gosh, divided by f of, oh sorry, minus okay, there it is. Let's make it purple. Oops. I know that seems like a lot of hassle, but this is really cool. This will help you visualize this. Okay. Let's have the x-axis go from -1 up to 4. Okay? So there's the secant line, right? Everybody agree? Okay, I'm going to put in the slope of the, oh, what did I just do? There we go. Let me put in the tangent line too. So that's going to be, this is just going to be gobbledygook to you. It's not going to make any sense right now. Yeah, it will. It will. It'll make sense. Okay, it worked. Good. So there's the equation of there's the tangent line, right? Everybody see that? The blue line? Everybody agree it's tangent?
Yeah.
Okay, so watch what happens here then. This is really cool. Watch what happens if I drag the value of delta x closer and closer. What do you notice happening? Yeah, everybody see that? Right? So the slope of the secant line, which is giving us the average rate of change. And if I pick a value, like let's set d to be 2 again. Okay? If I set d to be 2, what is the value of the difference quotient? Meaning what's the slope of, what's the average rate of change? That's that thing that we just wrote on the board. It's the slope of the secant line. It's just this thing right here. So you can't see that very well, but that says 4, right? That's telling me that the average rate of the change of the function on this interval from 2 or from 1 up to 3 is 4. Meaning if I'm going to go from there to there, I'm going to rise by, well, how do I rise by? I go from 1, I rise by 8, and I run by 2. 8 divided by 2 is 4, right? Okay, that's the average rate of change. What is the slope of the secant line, or the tangent line? Okay, so the slope of the tangent line is just given to us by, once again, this isn't going to make any sense right now, but just trust me on this, is 2. So the slope of the blue tangent line is actually 2. Because the function is increasing here, right? It's increasing at an increasing rate. The slope is always getting steeper. As I step to the right of my point of tangency, you see that the secant lines are going to get steeper than the tangent line, right? Because as we move along, the slope is getting, the curve's getting steeper and steeper, so we're moving up more and more quickly as we move to the right. Agreed? If I want to make an estimate of, without using calculus, if I want to make an estimate of the slope of that tangent line, all I got to do is drag d back towards 0. And what do you notice here? If you look at the values of, look right here in this box. Look at the slope of the secant line, the average rate of change. We're at 2.3, we're at 2.2, we're at 2.1, and then It's undefined there, right? I can't actually get to, why can't I do that? Well, what happens to this fraction if d goes to 0? Can't divide by 0. That's where, that sounds an awful lot like an indeterminate limit, doesn't it? I end up with f of c minus f of c over 0, which is just 0 over 0, right? So you're starting to get a hint here of how we're going to approach this, right? If we want to get a perfect estimate of the slope of the tangent line based on our secant line argument, we're just going to have to take a limit as what goes to 0. Okay, what about the secant line? So let me go back, let me get off of this page for a second. What's the limit going to do here as what goes to 0?
As the delta x.
Delta x, exactly, right? So the slope of a secant line is the average rate of change. And I'm going to write that because that's a big deal in math. We use that all the time. If we want to come up with the instantaneous rate of change, that's the slope of the tangent line, right? If we go back to our picture, the slope of the tangent line, that blue line right there, that's telling us what actually is the slope of the curve. And that's a weird concept, right? In calculus, we talk about slopes of curves. What's the slope of the curve when x equals 1? Remember, all curvature is eliminated if you zoom in infinitely far, right? If you were to beam somebody, that's, I don't know, from a different universe down into a wheat field around Pendleton, and you said, okay, our Earth is spherical, they'd say, you're crazy, it looks pretty flat. Wheat fields are just dead flat, right? Obviously, if you go further away, if you're on the moon, you can block the Earth out with your thumb. So the curvature, as you get closer, the curvature disappears. If I were to zoom in more and more on that one spot, I mean, we can see it happen. It's not like it's a great mystery. If I zoom in right here, look what happens. Pretty soon, that blue line of tangency is indistinguishable from the red curve, right? So you agree, it is the slope of the curve right there. If I zoom in infinitely far, so the curve loses all curvature, the lines are the same thing, okay? There it comes back to the curve. So we zoom out. Pretty soon, it looks awfully different from the curve. So the instantaneous rate of change is just defined as the slope of the tangent, which is just the limit of what we call the difference quotient. The difference quotient is the name we assign to the fraction that you get when you're calculating an average rate of change. So this whole thing in calculus and remember, you did some problems like this already, didn't you? I had you guys do some of these in the limit part earlier, where not knowing what it all meant, you were taking a limit of a difference quotient for different functions. So you've already done the heavy lifting associated with finding slopes of tangent lines. Here's the concept, here's why we did it. So the slope of a tangent line is the limit of the slope of a secant line as delta x goes to 0. More precisely, the slope of the tangent line is equal to what we call f prime of x, the derivative of the function f of x. Okay?
Does that say delta x equals to 0?
As delta x goes to 0. I can't read my writing. Okay? So let's use this, right? This is super cool. This was the birth of calculus, was this idea that you could find an instantaneous rate of change or the slope of a tangent line by doing this limit process. At the time, that was pretty revolutionary stuff. Now we've already talked about it in a high school class, but at the time it was a big, big deal.
I think Isaac Newton would feel about that his work is not considered worthy of a high school seat.
I I think you'd probably feel pretty good about that, I'm guessing. Okay, so let's take a function, let's take x squared. Take the one we just had. If we take f of x equals x squared, let's find the equation of line tangent to curve at x equals, well, let's just do 1. I already know the answer. Let's just do 1. Okay? How are we going to do that?
Plug 1 in for x.
Okay, well, for one thing, we know if I plug 1 in for x, f of 1 equals what?
Oh, yeah.
What's f of 1?
Both the difference quotient.
One.
1. Okay, so that tells us one important thing. That tells us that the point of tangency is at 1, 1, right? Do you see that? Okay, and if we look at, once again, if we look at our picture, there it is, there's our point of tangency at 1, 1. Scale's all messed up, but that's 1, 1. Right. And we need the slope though, right? If I had a point and a slope, I can write the equation of the line. So the only thing I'm missing is the slope of the tangent line. So how are we going to do that?
We're going to take the limit of these difference quotients.
Slope of the tangent is the difference quotient, right? Is the limit of the difference quotient. So we'll always start with this. It's the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. So we start general. That's our general form of the derivative, right? Slope of a tangent line. And now we get specific. Now we'll apply that to our specific problem. So what's f of x for us? X squared. Okay, so if f of x is x squared, let's rewrite this difference quotient for our function. What's f of x plus delta x? Well, but just in general, I don't want anything expanded out. Just make it simple here. What is it? X plus delta x squared, right? Well, I haven't plugged in 1 yet. X plus delta x squared minus f of x is x squared divided by delta x as delta x goes to 0. And you guys are pros at this, right? This kind of stuff is no big deal. What would we do to simplify this? Expand out. So x plus delta x squared is what?
X squared plus x, 2x delta x plus delta x squared.
Minus x squared over delta x as delta x goes to 0. Okay? What algebra do I have to do here? Okay, so I cancel horizontally. The x squareds subtract to 0, so those are gone. Now what? Factor a delta x out, right? And then we'll cancel like factors. And that gets rid of the 0 over 0 problem. Because I never tried this, but if I plug in delta x, you agree I'm getting 0 over 0, right? So we get the limit of delta x times what? 2x plus delta x. Everybody agree if I factor out a delta x?
Yeah.
Okay, divided by delta x. As delta x goes to 0, those cancel. We'll evaluate the limit when delta x equals 0. So that term goes away. And what's our answer? That's amazing. You got to appreciate that. What we just did there is phenomenal. We just found out a function that's going to predict the value of the tangent line for any value of x we choose. That's huge. So when x is 1, what's the slope of the tangent line? When x is 1,000, what's the slope of the tangent line? That's amazing, right? That tells you that's what that function does. So the slope of the tangent line at x equals 1 is just equal to f prime of 1, which is 2 times 1, which is 2. Well, now we have all the ingredients. We know a point of tangency. We know the slope is 2. And so This is pretty easy stuff, right? Then we just say y equals mx plus b, we can plug in m. So y equals 2x plus b, we'll use the solution x is 1, y is 1. To solve for b, so what's b? -1/2? Or -1, sorry. So if b is -1 and m is 2, y equals 2x minus 1 is the equation of the tangent line, and there it is. What do you know? Where's that crossing? At -1, right there.
So,
Yep.
so the derivative of a function is how the tangent slope changes in regards to.
It tells you the derivative function, and we'll talk much more about this over the next couple of days. The derivative tells us the slope of a curve for any value of x. That's its job.
Can you go to that page?
Which to, yeah,
One that you were
to
writing on?
that one?
Yes.
Okay.
That is cool. That is so cool.
Yeah, that's really cool stuff. I agree.
I won't
So-
be here tomorrow or Monday.
Okay, so hopefully that's going to be test days, which would be easy to make up. I'm assuming this is fixed. That's what we'll do. Is tomorrow we'll test it.
So would integral calculus be the reverse of that?
It's yes and no.